13.8 billion years ago, the cosmos burst into being. In a fleeting moment, nothingness transformed into everything. A pivot that redefines our reality. This enigma, the universe's birth, is science's greatest challenge, blending physics, philosophy, and mystery. All we know, stars, galaxies, laws, hinges on decoding how and why it began. Yet the origin eludes us, a cosmic riddle we're still solving. Some, like Stephen Hawking, claimed there was nothing before. Time itself sparked with the Big Bang. Imagine space-time folding back, curving until it vanishes, like seeking what's beyond the North Pole. Or perhaps there's no true beginning, only a limit to what we can perceive. Scientists point to inflation, a sudden explosive expansion in a split second that fueled the Big Bang, shaping all that followed. But what if inflation persists elsewhere, endlessly birthing bubble universes in a vast multiverse? Or maybe our cosmos is one cycle in an eternal rhythm, a big bounce, where universes expand, collapse, and renew, as physicist Paul Steinhardt proposes. Could our grasp of scale be wrong? Roger Penrose envisions a universe where the infinitely vast mirrors the infinitely tiny time and size merging. Or perhaps our reality is a spark from colliding dimensions. Superstring theory sees tiny vibrating strings in 11-dimensional hyperspace. Our universe, a single brain, caught in a cosmic clash. Maybe the answer hides in uncharted realms of math or physics, still beyond our reach. For now, the universe's origin remains an open question, a story with many paths. Yet 13.8 billion years ago, something ignited. This is the tale of what came next. Wherever you are on Earth, beneath the stars or city lights, tell us your place and time in the comments. Settle in for a cosmic journey. Where's the hottest place in the universe? You might think it's inside a star, where nuclear fires burn. But even the heart of a star, blazing at 15 million degrees Celsius, isn't the hottest spot. You could look to a supernova, the explosive end of a massive star, where gas bursts out, leaving a super-dense neutron star. Temperatures there hit 100 billion degrees Celsius, but that's still not the peak. The hottest temperature ever recorded was made on Earth, near Lake Geneva in Switzerland, at CERN's Large Hadron Collider. Scientists smashed lead atoms together at nearly the speed of light, creating a brief spike of 5.5 trillion degrees Celsius, 50 times hotter than a supernova. Yet even that isn't the hottest possible temperature. Temperature is just a measure of how fast particles move or vibrate. The coldest point, called absolute zero, is minus 273 degrees Celsius, where particles would freeze still if that could happen. But there's also a hottest limit, called the Planck temperature, about 1.4 times 10 to the 32nd Kelvin, where particles would break apart from their own energy. Max Planck, a German scientist from the early 1900s, gave his name to this extreme heat. His work started quantum physics, showing that light comes in tiny packets called photons. He also used universal rules, like the speed of light and gravity, along with his Planck constant, to define tiny measurements. The Planck length is the smallest possible distance, about 1.6 times 10 to the minus 35 meters, way smaller than a proton. The Planck time is how long it takes light to cross that tiny distance, 5.4 times 10 to the minus 44 seconds. The Planck temperature is the heat when thermal waves shrink to the Planck size. Nothing can get hotter. These numbers are hard to grasp. Our brains are built for everyday sizes, not these extremes. But these tiny units matter when we think about the universe's first moment. The universe is expanding, getting less dense over time. We don't know if it's infinite, but if it is, it always was. Instead of starting as a single point, it might have been huge, but packed tight. The observable universe, the part we can see, is limited by how far light has traveled since the Big Bang, 13.8 billion years ago. As we look back in time, this observable part shrinks, becoming super dense. At the very start, when it was just 1 Planck time old and 1 Planck length wide, everything in our observable universe was squeezed into that tiny space. Its temperature, the scorching Planck temperature, this moment, a fraction of a second after time and space began, is called the Planck era. It's a strange, wild time in the universe's story. The Planck era, a wild, strange time at the universe's start. Today, our world follows steady rules, shaped by 4 main forces: the strong force holding atoms tight, the weak force tied to some types of radiation, the electromagnetic force spreading energy far and wide, and gravity pulling everything together. Scientists like Max Planck showed that 3 of these forces, strong, weak, and electromagnetic, work through tiny packets like particles called gluons, W and Z bosons, and photons. But gravity, it's different. Albert Einstein changed how we see gravity, describing it as a bend in the fabric of space and time, not just a pull between objects. His ideas, tested many times, show gravity shapes the universe, affecting all matter and energy. But in the Planck era, when the universe was brand new, these normal rules didn't apply yet. Gravity was the first force to appear. Here's the catch. Einstein's gravity works for big things, like stars and planets. But in the Planck era, everything was squeezed into a space smaller than a proton. At that tiny scale, quantum mechanics takes over. A weird world where particles don't stay still, and looking at something changes it. Instead of solid answers, quantum rules deal in chances, and nothing stays the same for long. Luckily, this odd quantum world only rules tiny scales. In our everyday world, things average out to seem normal. But during the Planck era, everything was tiny, so quantum rules ran the show. The problem? Einstein's gravity and quantum mechanics don't mix. Scientists are hunting for a way to combine them, called quantum gravity, to explain how the Planck era worked. Testing this is tough. Studying other forces takes huge machines, like particle colliders, but probing gravity at that scale would need one as big as our solar system. Still, scientists keep thinking. One idea says gravity might use a tiny particle called a graviton to carry its force, but it's so weak we can't find it. Another idea, called loop quantum gravity, pictures space and time as pixel-like bits at the smallest scale, making gravity's math easier to handle. Then there's string theory, where particles aren't dots, but tiny vibrating strings. How these strings vibrate decides what they are, even gravity. But string theory needs extra dimensions, 10 or 11, folded up inside the strings or split into structures called branes, part of a bigger idea called M-theory. Each of these ideas stretches the mind, built on math that's hard to picture. Yet that's what we're doing, trying to imagine the universe's first tiny fraction of a second. In the 1950s, when quantum ideas were new, scientist John Wheeler gave us a way to picture the Planck era. He called it a quantum foam, a bubbling, chaotic mix driven by the unpredictable dance of quantum particles. This foam captures the wild, messy start of our universe. In the Planck era, the universe was a wild, chaotic place. A rule called Heisenberg's uncertainty principle made it impossible to pin down exact measurements of space-time or energy in this tiny cosmos. The smooth space and time we know today, gone. Instead, there was a strange, shifting quantum foam, a jumbled texture that changed without warning. Tiny black holes and tunnels in space, called wormholes, popped up and vanished in an instant with no clear reason. In this super hot, super tiny universe, anything could happen in the blink of an eye. But this wild time didn't last long. After just a fraction of a second, too small to imagine, the universe began to grow and cool. This marked the end of the Planck era and the start of a new chapter. The universe was still far from what we know today, but from this point, our science starts to make sense of what was happening. Everything in our universe is shaped by four main forces: gravity, electromagnetism, and the strong and weak nuclear forces. Picture yourself watching TV. Gravity keeps you in your chair, holds Earth's air close, and keeps our planet circling the sun, creating a cozy home for life. Yet gravity is gentle. You can lift a remote with just one hand. When you press a button, invisible light, electromagnetic energy, shoots from the remote to the TV. The screen lights up with tiny dots, sending more electromagnetic light to your eyes. Your eyes, amazing as they are, depend on atoms, tiny bits held together by the electromagnetic force. Inside each atom, the strong nuclear force glues protons and neutrons tight in the center. Even smaller, these protons and neutrons are made of tinier pieces called quarks, also held by the strong force. Every atom in you, the TV, and the whole universe relies on this force. As you watch the screen, your brain's nerves spark up to 200 times a second. This electric dance needs potassium, an element in your body. Like all elements, potassium is held together by the strong nuclear force, but it's also a bit radioactive. About 5,000 potassium atoms break down every second, a process driven by the weak nuclear force. Far away, 150 million kilometers from Earth, the sun's core burns bright, fusing hydrogen into helium. This powerful reaction heats our planet and creates the elements that make up you, the TV, and Earth itself. The weak nuclear force makes this possible too. It may sound weak, but its role is huge. These four forces, gravity, electromagnetism, strong and weak, work together to shape our world. For billions of years, they've defined the universe. But in the first tiny moment after the Big Bang, in the grand unification era, the rules were very different, built from the same basic pieces. Right after the Planck era, the grand unification epoch began, a time when only two forces ruled the universe. How could this be? Imagine flipping a coin. While it spins in the air, full of energy, you can't tell if it's heads or tails. It's just a blurry shape. Only when it stops do you see its true face. This is like the forces in the early universe. At super high temperatures, the weak nuclear force and electromagnetic force blend together, losing their separate identities. They become one force, called the electroweak force, a spinning mix of the two. Crank the heat even higher, and the strong nuclear force joins in, merging with the electroweak to form a single electro-strong force. This blending, called grand unification, unites three of the universe's four main forces: Scientists haven't fully proven this idea yet. Particle colliders can hint at the electroweak force, but joining the strong force needs a million times more energy, far beyond even supernovas or black hole jets. And gravity? It might join this unified force, but that's a mystery tied to the Planck era and quantum gravity. Still, grand unification helps explain the universe's first moments. For a time, 10 million times longer than the Planck era, the universe grew and cooled. Yet it was still tinier than a quark, a speck of matter we know today. With all that energy packed tight, the temperature soared to 100 billion trillion Kelvin, way hotter than anything we can create. In this grand unification epoch, the electro-strong force ruled a chaotic scene. Particles went wild, changing identities. Photons, bits of light, turned into matter and antimatter pairs, like quarks and leptons. But these particles barely lasted, switching back to photons in an instant. Special particles called electro-strong bosons added to the madness, turning quarks into leptons, matter into antimatter, and back again. It was a wild mix of energy and matter, real and fleeting. Then, a trillionth of a second later, the universe cooled to 1,000 trillion degrees. The strong force broke free, splitting the forces into three. Everything shifted again. But there's a catch. While these ideas explain the tiny particles in those early moments, they don't fully match the huge universe we see today. Something about the Big Bang's start seems off, not quite fitting the cosmos we know. Imagine a telescope peering deep into space. The James Webb Space Telescope, with its golden mirrors, gazed far into the universe's past, back to just 200 million years after the Big Bang. What it saw shocked scientists. Galaxies, already formed, looked far more organized than anyone expected. Astrophysicist Alison Kirkpatrick wrote that she lay awake at night, wondering if her ideas about galaxy formation were wrong. Soon, some news outlets twisted her words, claiming the telescope's images disproved the Big Bang itself. But that wasn't true. Kirkpatrick's worry was about how galaxies formed, not the entire universe. The Big Bang theory stood firm, but these early structured galaxies hinted at a missing piece in our understanding, a puzzle, not a crisis. Still, the Big Bang has faced bigger challenges. When we look at the universe today, things don't quite add up. Take its temperature. Stars burn at millions of degrees, while empty space is nearly as cold as absolute zero. Yet the average temperature across the universe, 2.7 Kelvin, is almost the same everywhere, no matter where you look. How can this be? The universe has been growing for nearly 14 billion years. Points more than 14 billion light years apart shouldn't have the same temperature because light, the fastest thing there is, couldn't have traveled between them to even things out. This sameness, called the horizon problem, suggests the universe started with an oddly uniform temperature, despite the chaotic tiny fluctuations in its earliest moments. Something doesn't fit. There's more to the universe's mystery. Einstein's theory of gravity says massive things, like stars and black holes, bend space and time, shaping how matter moves. Up close, these bends make space lumpy, but zoom out, and the universe looks smooth, almost perfectly flat. This flatness is strange. If the universe has lots of matter, space would curve inward like a ball, and gravity might pull everything back together in a big crunch. If there's too little matter, Space would curve outward like a saddle, and the universe would keep growing forever. Astronomers have studied this, and the universe seems flat, balanced just right. This is called the flatness problem, and it's as unlikely as a coin landing perfectly on its edge. There's another puzzle: magnetic monopoles. In the universe, electric charges come in pairs, positive and negative, balancing each other. Magnets work the same way, with north and south poles always together. But while lone electric charges like protons exist, we've never found a lone magnetic pole. A monopole. Why are they missing? In 1979, physicist Alan Guth found an answer that solved not just the monopole mystery, but also the horizon and flatness problems. Instead of growing slowly over billions of years, Guth said the universe inflated, exploding in size almost instantly. In less than a trillionth of a second, it doubled in size about 90 times, growing bigger than we can imagine. Think of folding a thin piece of paper in half, over and over. One fold makes it twice as thick, 2 folds, 4 times. By 7 folds, it's as thick as a notebook, 10 folds, as wide as your hand. If you could fold it 30 times, it would reach space, 100 kilometers up. At 42 folds, it would touch the moon. At 51, the sun. By 81 folds, it would span the Andromeda galaxy, and at 90 folds, like Guth's inflation, it would be bigger than a massive cluster of galaxies, 130 million light-years wide. This is what happened. After the wild Planck and grand unification eras, the hot, tiny universe exploded in size. This incredible growth in less than a trillionth of a second put the bang in the Big Bang. One moment, the universe was hot, packed, and buzzing with energy. Then in a flash, it stretched, becoming vast, empty, and cold. This sudden growth, called inflation, solves 3 big puzzles about the Big Bang. First, the horizon problem. Why does the universe have the same temperature everywhere? Inflation says the early universe was small and uniform, with all parts balanced in heat. Then it exploded in size, spreading those parts far apart. Our observable universe, 93 billion light-years wide, is just a tiny bubble of a much bigger cosmos. The parts we see stayed balanced, but other regions, beyond our view, might be wildly different. Next, the flatness problem. The universe looks flat, like a calm sea. But is it really? Inflation suggests we're only seeing a small piece. Far above Earth, you'd see its curve, but from the shore it looks flat. The whole cosmos might curve inward, outward, or twist in ways we can't see. Finally, the missing magnetic monopoles. Theory says these lone magnetic poles should exist, but we don't find them. But then inflation explains why. It stretched the universe so much that monopoles spread out, maybe one per observable universe. No wonder we haven't spotted one in 93 billion light-years. Inflation is now a key part of how we understand the universe's start. Since Alan Guth's idea 40 years ago, scientists have worked to explain how this massive growth happened. It began as the grand unification era ended, when the strong nuclear force broke free. Some think the decay of special particles, called X-bosons, created an inflating field. This energy drove the universe to double in size 90 times in less than a trillionth of a second. Tiny quantum ripples stretched into huge patches, setting the stage for galaxies and clusters. This expansion cooled the universe, dropping its energy 100,000 times. When inflation stopped, nobody's sure why, the inflation field faded, pouring energy back in a phase called reheating. This sparked the creation of matter in a bigger, roomier cosmos. The electro-weak epoch began, lasting until a trillionth of a second after the Big Bang. Quarks, leptons, matter, and antimatter swirled, ruled by gravity, the strong force, and the electro-weak force. But the universe was still too hot for these forces to fully shape it. Particles zipped around, ungoverned, because they lacked one key thing: mass. Another big change was needed to make the universe more like ours. Symmetry is all around us. In nature, we see balance and harmony. Our bodies, animals, even plants and tiny bacteria, are often mirrored down the middle or arranged in neat patterns like a starfish's 5 arms. Simple rules shape these balanced forms, making them easier to build than complex, uneven ones. In science, symmetry means things stay the same, no matter what. The laws of physics, the pull of gravity, the way energy works, they're steady across the universe. Positive and negative charges balance out. Some particles spin one way, others the opposite. Gravity feels the same here as it does on a distant star, but the universe isn't perfectly balanced. Like how our heart sits slightly to one side, the cosmos has flaws. Some particles only spin one way, never the other. There's more matter than antimatter. Electric and magnetic fields, though similar, don't act the same. These imbalances make our world work, but they weren't always there. In the first trillionth of a second, everything was perfectly balanced, symmetric. Then, as the universe cooled, the 4 forces split apart completely, and something new appeared: mass. Just as cooling water turns from vapor to liquid to ice, changing how it acts, the cooling universe changed its energy and matter. When the forces separated, a new time began, the quark era, where matter started to take charge. The biggest star we know, Uy Scuti, is huge, 1,700 times wider than our Sun. If it replaced our Sun, it would stretch past Jupiter. Yet it's made of tiny atoms, hydrogen and helium, the smallest building blocks. Long ago, people thought atoms couldn't be split, but we now know they can. Inside atoms are protons, neutrons, and electrons. Even smaller, protons and neutrons are made of quarks, tiny bits that, along with electrons, shape everything, from Uy Scuti to you. For 200 years, scientists have hunted for the smallest pieces of matter. Using giant machines called particle colliders, they smash particles together at incredible speeds. By studying the pieces, they built the Standard Model, a map of particles that explains why the universe looks the way it does. Normal matter, like protons and neutrons called hadrons, forms the world we see. Protons and neutrons, the heart of atoms, are made of smaller bits called quarks. Each quark has its own traits: mass, charge, spin, and something called color, which isn't about hue, but how quarks stick together. A proton with a positive charge has 2 up quarks and 1 down quark. A neutron with no charge has 2 down quarks and 1 up. There are other quirky quarks, like strange, charm, top, and bottom, forming rare particles seen only in lab experiments. No matter how hard scientists smash particles in colliders, quarks seem to be the smallest bits. Nothing smaller shows up. Electrons, which zip around atoms, are also tiny and unsplittable. They're part of a group called leptons. Besides electrons, colliders reveal heavier leptons like muons, tau particles, and neutrinos. The Standard Model maps out 12 core particles, 6 quarks, and 6 leptons, plus their antimatter twins. Add to that the force carriers, photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. Gravity's carrier, if it exists, is still a mystery. These particles and forces explain almost everything in our universe. But one piece is missing: mass. Every element, from hydrogen to gold, has a specific weight, mostly from protons and neutrons. But here's the twist. A proton's mass isn't just the sum of its quarks. Quarks make up only 9% of a proton's weight. The rest? It's energy locked inside, tied to Einstein's famous E equals E squared, and the wild dance of gluons in the strong force. So most of an atom's mass comes from energy, not stuff. Still, quarks do have some mass, unlike photons or gluons, which have none. Electrons and neutrinos have tiny masses, but W bosons are heavy, 40,000 times heavier than an up quark, more than an iron atom. Why do particles have such different masses? Why do they have mass at all? In the 1960s, physicist Peter Higgs puzzled over this. He proposed that at the universe's start, all particles had no mass. Then, in the first billionth of a second, a new energy field, the Higgs field, spread across space. This field gave particles their mass, carried by a special particle called the Higgs boson. This boson joins the Standard Model's 16 particles, shaping how matter works in our universe. Peter Higgs's idea about the Higgs field was brilliant, but finding the Higgs boson took nearly 50 years. To explain why this search mattered, a UK science minister in 1993 offered champagne for the best analogy. Many tried, talking about syrup or electric fields, but physicist David Miller won with a lively party scene. Imagine a crowded party. A regular person slips through the room easily, barely noticed, but when a famous scientist enters, everyone swarms, slowing them down with chatter. The partygoers are like the Higgs field, giving the scientist representing a particle mass. The buzz of the crowd as people share news of the arrival acts like the Higgs boson rippling through. It's not a perfect picture, but it's stuck. Finding the Higgs boson was like hunting a needle in a haystack without knowing what the needle looked like. Giant machines, like the Tevatron in America and the Large Hadron Collider in Europe, smashed particles for years. Higgs's theory didn't say how much energy was needed or what the boson would be like. But in 2012, the Large Hadron Collider found it. Scientists confirmed the Higgs boson existed, proving the Higgs field was real. It earned its spot in the Standard Model, shaping the universe's story. A trillionth of a second after the Big Bang, the electro-weak force split apart, shattering the universe's perfect balance. The W and B bosons, which carried this force, turned into photons for electromagnetism, and W and Z bosons for the weak force. This was just the start of the change. The Higgs field appeared, giving mass to particles created in the chaos of inflation, and the force split. U and Z bosons became heavy. Quarks and leptons gained mass based on their type, but photons and gluons stayed massless, untouched by the Higgs. By a billionth of a second, the quark era took shape. The universe now held all the pieces, particles and forces, needed for stars, planets, and us. A mix of quarks and gluons, like a cosmic soup, filled the growing universe, ready to form everything we know. Our universe is bursting with variety. Stars blaze fast and explode in 1,000,000 years, or glow gently for trillions. Planets come in all kinds: huge gas giants, scorched rocky worlds, or rare green, life-filled ones like Earth. On Earth, life thrives in endless forms, from tiny bacteria breathing sulfur to clever apes building telescopes, wondering about the cosmos. In the vast universe, there's room for endless differences, but some things never change, no matter where you are. These are the constants of nature, fixed rules that shape how the universe works. Scientists have found these rules one by one, like the speed of light, a steady 300 million meters per second, the fastest anything can go. Or gravity's strength, a tiny number that pulls objects together always the same. Other constants set how particles carry energy, how magnetic fields form, or how electric charges spark fields. Even the masses of tiny particles, like quarks and electrons, are fixed, but nobody knows why. Not even the Higgs field explains it. Why do these numbers have the values they do? Take the fine structure constant, a number around 137, which controls how strongly particles like electrons interact with light. There's no reason it couldn't be 12 or 3,000, but if it were different, protons might fall apart, and matter wouldn't hold together. Other constants are just as picky. If gravity were weaker, the universe would be a thin soup of gas. If stronger, everything would collapse into black holes or short-lived stars, leaving no room for planets or life. These constants seem random, but are perfectly tuned for our diverse universe. Why? Nobody knows. Is it luck? A creator's design? Or, as some scientists think, is our universe just one of many, each with different rules? Most might be empty, lifeless flops, but yours, with its just right constants, grows stars, planets, and us. This fine-tuning mattered right from the start. By a billionth of a second after the Big Bang, the universe was packed with quarks, leptons, and fleeting particles, but it was still too hot for them to do much. By a millionth of a second, it cooled to 1 trillion degrees Celsius. Quarks and gluons slowed down, finally able to stick together. Protons and neutrons, each made of 3 quarks, began to form. But the quarks in a proton, 2 up and 1 down, don't naturally fit together. Inside a proton, things get strange. Up quarks, both positively charged, push each other away, like magnets repelling. It takes the strong nuclear force, carried by gluons, to hold them tight with a down quark, forming a stable proton. But protons are weirder than that. Most of their mass, about 99%, comes from energy, not the quarks themselves, thanks to wild quantum dances inside. Sometimes, a quark can briefly turn into a heavier charm quark and its antimatter twin, then snap back. This means protons are a shifting mix of normal quarks, gluons, and fleeting charm quarks, mostly made of particles that barely exist. In the first millionth of a second, protons and neutrons became key players in the universe. But the weak nuclear force kept things chaotic, letting protons flip into neutrons and back again. As the universe cooled, nearing 1 second old, this flipping slowed down. During this freeze-out, protons and neutrons picked their final forms. Here, the universe's fine-tuned rules shone. Down quarks, slightly heavier than up quarks, make neutrons, 2 downs and 1 up, a bit heavier than protons with 2 ups and 1 down. As the cosmos cooled, it was easier for heavy neutrons to become lighter protons than the other way around. This tipped the balance, leaving about 7 protons for every neutron. This ratio shaped our universe. Protons, the core of hydrogen and helium, fuel stars, and build heavier elements. Their abundance over neutrons sparked the chemistry that led to life. If down quarks were lighter, neutrons would have outnumbered protons. Without enough protons, hydrogen, one proton, no neutrons, wouldn't last. Some heavier elements, like helium, might form, but helium doesn't react easily. With mostly unreactive neutrons, stars and planets couldn't form, leaving a cold, dark, lifeless universe. We're lucky for this proton-heavy balance. But another mystery appeared, a strange shortage of antimatter. Imagine a far-off alien world where a civilization builds a superweapon. They master antimatter, particles opposite to normal matter, trapping it with magnetic fields. When antimatter meets matter, they destroy each other, releasing huge energy. This power could end their world in a flash, seen from Earth as a faint star's glow. Antimatter is powerful. When it touches normal matter, they destroy each other, releasing huge energy. Just 1 gram of antimatter could match a nuclear bomb needing 90 kilograms of fuel. Imagine an alien world stockpiling antimatter, leading to a blast that wipes out everything. Night turning to day, cities burned away. This shows antimatter's danger, and it's all around us. In 1928, physicist Paul Dirac predicted antimatter while mixing Einstein's ideas with quantum physics. His math suggested a particle like an electron, but with a positive charge, a positron. In 1932, Carl Anderson found it using a cloud chamber to catch cosmic rays. By the 1950s, labs in California spotted antiprotons and antineutrons. In 1995, scientists built an antihydrogen atom. Antimatter shows up in exploding stars, black hole jets, even in bananas, where potassium decays into positrons every hour or so. But normal matter far outweighs antimatter. In our galaxy, there's maybe 1 antimatter particle for every quadrillion normal ones. This imbalance saved the universe. Equal amounts of matter and antimatter would have wiped each other out, leaving no stars or planets. But why is there so little antimatter? In the first billionth of a second, matter and antimatter formed in pairs from energy bursts. In that dense, hot cosmos, they quickly met and vanished, turning back into energy. As the universe cooled, gluons built protons and neutrons, and equal amounts of antiprotons and antineutrons. Everything should have stayed balanced. Matter and antimatter act the same, created and destroyed in pairs, so their amounts should have matched. But they didn't. Between a millionth of a second and 2 minutes after the Big Bang, something shifted. Only 1 antimatter particle in a billion remained. Why? Scientists aren't sure. One clue might be the weak force. In the 1950s, Chien-Shiung Wu showed it treats quarks and antiquarks slightly differently. This tiny difference matters, but it's not enough to explain why matter won out. Another idea points to a hidden particle. Most particles come in left-handed and right-handed forms, like mirror images, but neutrinos break this rule. We only see left-handed neutrinos and right-handed antineutrinos. What about the missing right-handed neutrinos? Some think they existed in the first millionth of a second but vanished, possibly decaying into more matter than antimatter. This could have tipped the scales. It's a tempting idea, but hard to prove without finding those lost neutrinos. We'll need to wait until the universe is about 1 second old for neutrinos to reveal more. When we look deep into the night sky, wonders fill our view. Galaxies swirl, nebulae glow with color, and bright spots called quasars, huge black holes devouring matter. shine from the hearts of distant galaxies. These quasars reveal something else: the Lyman alpha forest. Light travels at a fixed speed, so the farther we look, the further back in time we see. Quasar light from billions of years ago stretches into redder colors as the universe expands. But their light shows more than just this redshift. At shorter wavelengths, we see dips in the light, sometimes so many they look like a thick forest of pine trees on a mountain. This Lyman alpha forest comes from faint clouds of hydrogen gas floating in space. When quasar light passes through these clouds, some gets absorbed, creating those dips we see on Earth. Each dip marks an invisible hydrogen cloud, showing us the early universe's makeup. These dips are strongest in the oldest, most redshifted light, telling us the early cosmos was packed with hydrogen clouds, nurseries for stars and galaxies, born in the universe's first moments. By 1 second after the Big Bang, a lot has happened. The universe cools to 10 billion degrees Celsius. It's filled with particles that survived fierce battles, plus bursts of light from matter and antimatter wiping each other out. The balance of protons and neutrons is set, and the wild creation of new particles slows down. Thanks to the Higgs field, particles have mass. The four forces, strong, electromagnetic, weak, and gravity, now work as we know them, though still a bit wild in this hot, energetic cosmos. Until now, this early universe was mostly for theoretical physicists, as our machines can't recreate those extreme energies. But at 1 second old, the universe becomes something we can study with experiments and telescopes. We're starting to see and map our cosmic past. In Antarctica's icy wilderness where the sun stays up for weeks, scientists began a bold project in 2005. At the Ice Cube Neutrino Observatory, they sprayed hot water to drill a 2.5-kilometer deep hole in the ice, a 58-hour task. It was the first of 80 holes, spread over a square kilometer, building a one-of-a-kind telescope. The Ice Cube Neutrino Observatory doesn't look up at the stars. It peers down through the Earth itself. No lenses or mirrors here. Instead, over 4,000 sensors hang on 80 strings, deep in Antarctic ice, like glowing beads in the dark. This odd setup is perfect for catching one of the universe's slipperiest particles, the neutrino. Other projects hunt neutrinos too, in gold mines under deep lakes or inside Japanese mountains. Neutrinos are ghostly. In the 1930s, Wolfgang Pauli suggested they exist to explain missing energy when a neutron decays into a proton and electron. So tiny and light, they seemed impossible to detect. About 100 trillion neutrinos zip through your body every second, unnoticed. In 1951, physicists Clyde Cowan and Frederick Rines refused to give up. Their Project Poltergeist aimed to spot neutrinos using nuclear reactors' energy. They first imagined a massive detector near a nuclear blast, hoping to catch a neutrino's faint light flash. Too risky, they switched to safer reactors and in 1956 found the neutrino, a breakthrough after 20 years of mystery. Today, scientists make and study neutrinos in powerful machines, but huge detectors like one in Lake Baikal still help. Neutrinos reveal secrets about the universe's start and its wildest events. In 1987, a star in the Large Magellanic Cloud exploded as a supernova, sending neutrinos to Earth. Scientists in Japan caught just 11 of them, but it sparked a new way to study the cosmos, combining neutrinos with light and gravity waves. Neutrinos slip through stars, planets, and nebulae, barely touching matter, thanks to interacting only with the weak force and gravity. This makes them perfect for peering into places light can't reach. Just 1 second after the Big Bang, the universe was a hot, dense fog of particles and light, too thick for telescopes to see through. This fog hid the cosmos for hundreds of thousands of years, but neutrinos could escape. At 1 second old, the universe cooled to 10 billion degrees Celsius. Particles slowed, and neutrinos stopped bumping into others. They broke free, streaming through the chaos, leaving a faint trace of the universe's earliest moments. If we could catch the cosmic neutrino background, it would be like a snapshot of the universe at just 1 second old, 380,000 years earlier than what light can show us. These ancient neutrinos are trickier to find than the high-energy ones. While 100 billion high-energy neutrinos fill every cubic centimeter of space, only about 300 from that first second remain. To spot them, we'd need detectors a billion times more precise, or we could look for their faint echoes. When neutrinos broke free in that early foggy cosmos, they left tiny ripples like sonic booms, making some spots slightly hotter, others cooler. Over 13.8 billion years, these ripples stretched into the vast patterns of galaxies we see today. By studying these patterns, we might hear the echoes of a 1 second old universe. Another mystery from this time involves TON 618, a monster 18.2 billion light years away. It shines 140 trillion times brighter than our sun, powered by a black hole 66 billion times heavier than the sun, bigger than all the Milky Way's stars combined. Its pull is so strong that matter spirals in at 10,000 kilometers per second, glowing hot as it's swallowed. Supermassive black holes like this live at the hearts of big galaxies, shaping how they grow. But there's a problem. Some appeared just a few million years after the Big Bang. Too big, too fast. Our models say they shouldn't have grown to 1 billion solar masses so soon. Only about 100,000 solar masses should have been possible. In 1971, Stephen Hawking had an idea. Primordial black holes. These formed not from dying stars, but from dense clumps in the early universe's hot plasma. During a brief window, about 1 second after the Big Bang, gravity crushed these clumps into black holes before the universe cooled and spread out. After that, new black holes had to wait millions of years to form from stars. These primordial black holes might explain those early giants, but how big were they? Estimates range from tiny specks, lighter than a paperclip, to beasts 100,000 times heavier than the sun. Finding them is tough. Hawking suggested black holes lose mass through Hawking radiation, especially small ones. Tiny black holes could vanish in a blast, equal to 1 million megaton bombs. Scientists search for these explosions with tools like the Fermi Gamma Ray Telescope, or look for stars bending light as black holes pass by, or even stars crushed by their gravity. So far, we've only narrowed down their possible sizes. Hope isn't lost. The James Webb Space Telescope is hunting early stars and galaxies, possibly spotting signs of primordial black holes. Next decade, LISA will listen for gravitational waves. Some may be from black holes born just 1 second after the Big Bang. On December 5th, 2022, scientists at California's National Ignition Facility did something incredible. They aimed 192 lasers at a tiny gold cylinder holding a peppercorn-sized pellet of 2 hydrogen types, deuterium and tritium. The lasers heated the cylinder to 3 million degrees Celsius, hotter than the sun's surface, blasting X-rays that crushed the pellet at 400 kilometers per second. The fuel squeezed to 100 billion times Earth's air pressure in a flash, fusing deuterium and tritium into helium, releasing a neutrino and extra energy. The lasers used 2.05 megajoules. The reaction gave back 3.15 megajoules, a 50% energy gain. For the first time, humans created a fusion reaction that gave more energy than it took, enough to boil 20 kettles, hinting at a future of clean power. Stars have done this for billions of years, and the universe mastered it in its first minute. Humans love transforming one thing into another, like pulling flowers from thin air or turning dull metals into gold. In the early universe, wild forces swapped particle identities, and even now transformations happen. The weak force drives radioactive decay, breaking atomic nuclei into lighter elements, like carbon-14 for dating old bones, or uranium-235 for nuclear power. This decay happens on its own, but nuclear fusion, building heavier elements, is tougher. An atom's identity depends on its protons and neutrons. Hydrogen has one proton. Its versions, protium, deuterium, tritium, add neutrons, doubling or tripling the mass. Add another proton, and it becomes helium, with helium-4, 2 protons and 2 neutrons, being the most stable. The strong nuclear force glues these particles into nuclei, but protons, all positively charged, push apart due to the electromagnetic force. It takes extreme heat and pressure, like in stars or that gold cylinder, to shove protons close enough for the strong force to bind them into new elements. Heavier elements, with dozens of protons, need even wilder events, like exploding stars to form. Scientists have long studied how stars fuse hydrogen and helium into new elements, even in failed stars called brown dwarfs. These gas giants, bigger than Jupiter but smaller than stars, can't fuse regular hydrogen, but manage it with heavier deuterium. Yet where did deuterium and helium come from? Not from stars. They appeared in the universe's first minute. A microsecond after the Big Bang, at 10 trillion degrees Celsius, quarks formed protons and neutrons, the seeds of all elements. But stars with their fusion furnaces didn't shine for 100 million years. So how did the first atomic nuclei form? In 1948, Ralph Alpher, a brilliant PhD student, and his mentor George Gamow, proposed Big Bang nucleosynthesis. Their paper, humorously co-credited to Hans Bethe for an alpha-beta-gamma joke, explained how the early universe's heat fused hydrogen into helium through deuterium. Protons, the simplest hydrogen nuclei, formed right away. Full hydrogen atoms with electrons came later. By 10 seconds, the universe cooled enough for deuterium, 1 proton, 1 neutron, to form, but it was too hot to last. Photons smashed these nuclei apart, creating a deuterium bottleneck. After 300 seconds, temperatures dropped, stabilizing deuterium. Under the universe's crushing pressure, deuterium fused with protons, creating helium-3, a new element. Next came helium-4 with 2 protons and 2 neutrons, the toughest nucleus to break. Most free protons got locked into helium-4, making the universe about 25% helium by mass, a ratio we still see today, proving Alpher's idea. This was another lucky break. If protons and neutrons had balanced differently, or if the early universe was denser, too much helium would have formed. A helium-heavy universe, too stable to react, would have no chemistry, no stars, no us. Even with lots of helium, the universe buzzed with energy for more fusion. For 1200 seconds, 20 minutes, this cosmic furnace raged, forging new elements. Then, it cooled too much to continue. Only hydrogen, helium, lithium, and a bit of unstable beryllium existed. Beryllium faded fast, leaving just the first 3 to fuel the stars that later made all 98 natural elements. The early universe had 12 hydrogen nuclei for every helium-1, and 1 billion photons for every particle. With these ingredients, the cosmos was ready to build everything, including the deuterium fused in labs 13.8 billion years later. Life is a chemical marvel. As far as we know, it's only sparked on one ordinary wet, rocky planet orbiting a typical yellow star in a quiet corner of the Milky Way. How did life begin on Earth? Fossils trace back 3 billion years, but the moment life ignited is lost in time. Biologists know life depends on organic molecules, built from carbon, oxygen, and hydrogen. All living things share a chemical blueprint in DNA and RNA, made of repeating units called nucleobases: cytosine, guanine, adenine, thymine, and uracil. These code the instructions for a leaf, a wing, or a strand of hair. But where did these molecules come from? Some think Earth's warm, chemical-rich pools cooked up organic molecules from scratch. Others believe the seeds of life formed not on Earth, but out among the stars. Evidence for this cosmic origin is growing. In 1969, astronomers in West Virginia, using the National Radio Astronomy Observatory, caught the faint hum of formaldehyde, a mix of carbon, hydrogen, and oxygen in deep space. Since then, over 250 complex organic molecules, like aldehydes, alcohols, and amines, have been found in starry clouds and around distant stars. These are the building blocks of life, floating in the empty cosmos. An even bigger clue landed in 1864. On May 14th, near Orgueil, France, a meteorite crashed in 20 pieces. Scientists found it was like peat, hinting at organic matter. Debates swirled. Could it hold life? No clear signs of biology were found, but in the 1960s, with better tools, chemists discovered adenine and guanine, nucleobases matching those in DNA and RNA. Meteorites like Murchison in Australia, Murray in Kentucky, and Tagish Lake in Canada reveal more nucleobases: cytosine, thymine, uracil, plus others not used in Earth's life. These finds hint at a cosmic truth. The universe, on its own, brews complex molecules. This space chemistry began less than 100,000 years after the Big Bang. After 20 minutes, Big Bang nucleosynthesis stopped as the universe cooled. It was still denser than air, too hot for electrons to join nuclei. The cosmos was a buzzing plasma with more energy than matter, and stayed that way for tens of thousands of years. But something stirred in the chaos. In 1925, scientists made helium hydride in labs, an unstable mix of helium and hydrogen. In 1978, astrochemist John Black predicted it could form in space, in glowing clouds from dying stars called planetary nebulae. There, charged helium might steal electrons from neutral hydrogen, forming helium hydride. For years, it stayed hidden. Then, in 2019, the SOFIA telescope, a 2.7-meter mirror on a Boeing 747 flying above 43,000 feet, spotted it. High above Earth's water vapor, SOFIA's great receiver caught helium hydride's faint glow in a nebula 3,000 light-years away in the Cygnus constellation. This find, after nearly a century of searching, confirmed Black's idea. The nebula's hot, charged conditions mimicked the early universe. Though this helium hydride wasn't from the Big Bang, it showed how it could form back then. After nucleosynthesis, high energies kept hydrogen and helium as charged ions. Around 100,000 years, at 4,000 Kelvin, things changed. Helium, the least reactive element, needed huge energy to lose electrons, so it grabbed them first, forming neutral atoms. But it was too hot for protons to make hydrogen atoms. Instead, protons clung to helium, sharing electrons. This created the universe's first molecule. Helium hydride ions. Short-lived and unstable, they sparked the first chemical bonds. These fragile ions opened the door to more molecules, kicking off space chemistry. Today, astrochemistry studies cosmic molecules, like water, ammonia, and odd ones, like H2Cl+, or HO2. All trace back to those first helium hydride ions, born and broken in the universe's first 100,000 years. We think we know the world around us. Our eyes catch light, ears hear sound, and hands feel matter's touch, but we miss so much. Visible light is just a sliver of the electromagnetic spectrum. High-energy gamma and X-rays spill from our food, homes, even our bodies. Sunlight, which seems familiar, hides 10% ultraviolet rays that can burn skin and eyes, and 50% infrared, felt as heat. Warm objects glow infrared, invisible to us. Motion sensors, TV remotes, Wi-Fi, and GPS use microwaves, while radios ride long radio waves, all washing over us unseen. If we saw it all, the night sky would dazzle with color, hum with gravitational waves, and glow faintly with the universe's first light. For 380,000 years, the universe was a foggy trap for light. From a trillionth of a second after the Big Bang, photons, bursts of energy, were stuck in a dense swarm of particles. As the cosmos cooled, energy turned into matter, filling space with vibrating subatomic bits, too thick for light to pass through. Nothing changed until atoms formed. Today, neutral atoms, not charged ions, build everything. A single human body holds 7 octillion atoms, a 7 with 27 zeros. Scale that to Earth, then to all planets and stars, and the universe's atom count is beyond imagining. The key to atoms is electrons. Found in the late 1800s, these tiny negatively charged particles are 2,000 times lighter than protons, acting like shapeless points. Quantum rules make them slippery. We can't pin down their speed and spot it once. They seem to exist everywhere physics allows. After Big Bang, nucleosynthesis made atomic nuclei. The electromagnetic force pulled electrons to these positively charged cores, forming neutral atoms. Forming atoms sounds simple. Hydrogen nuclei grab 1 electron, helium nuclei grab 2. But it's not quick. The electromagnetic force, 100 times weaker than the strong force holding nuclei together, needs a cooler universe to tame wild electrons. After 380,000 years, at 3,000 Kelvin, the cosmos cools enough for electrons to settle into orbits around nuclei. This changes everything. Electrons, once roaming free, now lock onto positively charged nuclei, clearing space in the universe for the first time. Photons, trapped for eons in a dense particle maze, suddenly break free, streaming in straight lines. This is the universe's first light. The cosmos shifts from opaque plasma to transparent gas, from scattered chaos to whole atoms. For the first time, we could see the universe. Scientific breakthroughs are rarely accidents. They come from years of hard work, but in 1978, the Nobel Prize went to Arno Penzias and Robert Wilson for a fluke discovery. In the 1960s, at Bell Labs in New Jersey, they used a 20-foot horn antenna built for satellite signals but left obsolete. They aimed to study faint radio waves from the spaces between galaxies. Instead, they heard a stubborn hiss coming from everywhere. It wasn't New York City, nearby military bases, or any part of the Milky Way. They checked the antenna, finding pigeons nesting inside, their droppings possibly causing the noise. After clearing the birds, the hiss persisted. Penzias and Wilson ruled out every error. Could this noise really come from the entire sky? They asked astronomer Robert Dicke for help. Dicke had a theory. After the Big Bang, as the universe cooled, atoms formed in a process called recombination, making the cosmos transparent. This released a burst of light, once yellow-orange, now stretched by cosmic expansion into microwaves. Penzias and Wilson had found it, the cosmic microwave background, by chance. Dicke planned to search for it, but they beat him to it. In 1978, the Nobel went to Penzias and Wilson for this cosmic echo, a glimpse of the universe at 380,000 years old. The cosmic microwave background, CMB, found by Penzias and Wilson, changed everything. Though Robert Dicke's idea of a cycling universe didn't hold, the CMB's faint glow, now just 2.7 degrees above absolute zero, proves the Big Bang started hot and dense at 380,000 years old. It's the earliest snapshot we have, showing a packed, energetic cosmos and hinting at its future. Penzias and Wilson heard a steady hum across the sky, but later telescopes like the Cosmic Background Explorer, Wilkinson Microwave Anisotropy Probe, and Planck found tiny hot and cold spots, varying by mere millionths of a degree. These maps revealed density patches, seeds for today's galaxies. Denser spots pulled in more matter, growing over 100 million years into the first stars and galaxies. These patches, born from quantum flickers stretched huge in the Big Bang's first instant, seem random, but hold a hidden pattern. Before atoms formed, the universe was a thick plasma where sound waves, baryonic acoustic oscillations, rippled through. Gravity tugged matter into dense clumps, but trapped photons pushed back, creating outward ripples like raindrops on a pond. When the universe cooled to 3000 Kelvin, electrons joined nuclei, forming atoms. Photons escaped, freezing these ripples in place. The matter at their edges stayed, locked in spherical shells. Today, 13.8 billion years later, these frozen ripples shape galaxy clusters, now 500 million light-years wide. Their size acts as a standard ruler, letting astronomers measure how fast the universe expands. With this, we can trace the cosmos's past and predict its future. The CMB's glow, though dimmed and stretched, will linger for trillions of years, offering clues to future scientists. In the dark, a spark of light signals the birth of stars. A single star flickers, then another, until a cascade of light sparks a cluster. It grows, spinning faster, stretching into a disk whirling at 200 kilometers per second, turning fully every 250 million years. This young spiral galaxy, our Milky Way, swallows smaller clusters, merging with others to fuel bursts of star formation. 10 billion years ago, it thrives. In its spiral arms, massive stars blaze, burn out, and explode, scattering heavy elements, forged in their cores, back into the galactic cloud. These enrich the gas, birthing new stars, and, for the first time, planets. Around 4.6 billion years ago, on a quiet spiral arm 25,000 light-years from the center, a yellow star forms. Dust and gas swirl around it, clumping into pebbles, then boulders, then rocky worlds. After chaotic collisions, these worlds settle into orbits, stable for billions of years. On the third planet, Earth, heat from its violent birth fades. Water pools into oceans, atmospheres form, and plates of rock shift. In those oceans, a spark of life ignites, evolving into countless creatures that fill sea, land, and sky. Chemistry turns to biology, and eventually, a thinking mind ponders its place in the cosmos. We know this rough story: Milky Way, Sun, Earth, life, us. But gaps remain. How did the clumpy soup of atoms, formed 380,000 years after the Big Bang, lead to all this? Was it certain, or could the universe have taken another path? Simulations using the matter and energy from that time create a universe with fewer galaxies, slower star formation, and delayed planets. Life might lag or never appear. Something's missing, a hidden piece that ties it all together. This piece is invisible. At 380,000 years, light escapes the dense fog of the early universe, but the cosmos dims. Photons lose energy as space expands, and no new light sources exist yet. Nuclear fusion in stars is millions of years away. These are the universe's dark ages, quiet but not still. During the universe's dark ages, up to 1 million years after the Big Bang, dark matter takes center stage. In 1933, Fritz Zwicky studied the Coma Cluster, 320 million light-years away. Its galaxies moved too fast to stay together based on the visible star's mass. Zwicky suggested invisible dark matter, or Nuclei materie, added the needed heft, 10 times more than what we could see. In the 1970s, Vera Rubin saw something similar in the Andromeda Galaxy. Stars at its edges spun as fast as those near the center, defying expectations. Rubin calculated visible matter was only 15% of the galaxy's mass. A vast, unseen halo of dark matter, up to 15 times larger than the visible Milky Way, must surround it. Most galaxies, including ours, have these halos. Dark matter outweighs normal matter 6-to-1, shaping the cosmos, yet we can't see it. What is it? One idea is MACOs, massive, compact halo objects, like black holes, dense neutron stars, or brown dwarfs that don't shine enough to spot. But as telescopes improve, finding enough MACOs to explain dark matter seems unlikely. Instead, many favor WIMPs, weakly interacting massive particles. These mysterious particles, outside our standard model, only interact via gravity and have high mass or numbers to account for 85% of the universe's mass. Despite searches in particle accelerators in space, WIMPs remain hidden. Whether MACOs, WIMPs, or something else, dark matter likely formed in the Big Bang's first moments. By 1 million years, during the Dark Ages, it began sculpting the cosmos. The cosmic microwave background shows uneven matter and energy patches at 380,000 years. Dark matter, clumped similarly, started pulling the universe into shape. Dark matter clumps faster than normal matter, drawn by gravity into dense pockets. Normal matter follows, sinking into these invisible wells, forming vast filaments, nodes, and clusters, cradles for the first stars and galaxies. By 1 million years, the universe's path is set. The four forces, gravity, electromagnetism, strong and weak, are distinct, governing all interactions. Matter's mix, set in the Big Bang's first moments, fuels stars, galaxies, chemistry, and life. For 8 billion years, everything unfolds as expected. But 5 to 6 billion years ago, just before our solar system formed, something shifted. In 1998, astronomers studying supernovae, standard candles with predictable brightness, noticed they were more redshifted than expected. Their light, stretched by expanding space, showed the universe's expansion wasn't just continuing. It was speeding up, a trend echoed in galaxy clusters and baryonic acoustic oscillations. This acceleration is growing. The culprit? Dark energy. Since our solar system's birth, we've lived in a dark, energy-driven era. But what is it? Einstein's cosmological constant, an energy in empty space, might explain it. As space grows, this energy increases, pushing expansion faster. Though Einstein dropped the idea, it fits dark energy. Yet why this energy exists is unclear. Another clue might lie in quantum vacuum energy, where fleeting virtual particles pop in and out, pushing space outward. But calculations overshoot, predicting far too much expansion. Some propose quintessence, a strange energy field that can pull or push, changing over time. Without ways to test it, we're left guessing. Today, the universe is roughly 68% dark energy, 27% dark matter, and just 5% normal matter. From these, guided by rules set in the Big Bang's first trillionths of a second, our cosmos grew over 13.8 billion years. As the universe expands, driven by the unseen hands of dark energy and dark matter, it carries the story of its birth. 13.8 billion years of creation, from a spark of light to the galaxies we call home. We are part of this cosmic tale, born from the same stardust, pondering our place under the stars. What mysteries do you think the universe still holds? Share your thoughts below, and let's dream together of what lies beyond. Until next time, rest under the cosmic canopy and let the stars guide your wonder.